Okay, just in case anyone's bored tonight, like you're not into watching Philadelphia and whoever they're playing, you do have another option for football. You have Jordan's, what's your team's name, Jordan?
Bissell.
Jordan's Bissels versus Paris. Do you have a team that's more interesting?
Burners.
The Burners, all right. So I've got a mobile lawn, or I would come because, guys got duties to the family. Yeah, 7 o'clock. Okay, so I have first a problem. A student asked me a problem. This is, again, it's a bad precedent, really, to do problems that haven't been turned in yet. But I'm going to do a problem a student asked me to do that hasn't been turned in. And then 2 more slides on the Chapter 5 forces before we start Chapter 6. So a student asked me to look at this problem here. It's problem 3 from the homework that is due today. And so you can see the problem. It's a person pulling a block of ice. And it tells you the mass of the ice, gives you the angle of the person's pulling from, and then it has 2 questions: calculate the minimum force to get it to start sliding, and then what's the acceleration going to be once it starts sliding. So I wrote here some questions to get us thinking about this so we can solve the problem. So question number 1, what is the object of interest? So, and let me try to make sure I get the Southwestern students involved here. So somebody in the Southwestern classroom, tell us, what is the object of interest for this problem? I haven't heard an object yet. Okay, the block of ice. So the block of ice is our object of interest. And then we have to identify what forces are acting on that ice. So there's one already drawn, so I won't ask you to rename the force of him pulling. What other forces are acting on it? And I want all of them. Okay, there's a force normal. Since it's a horizontal surface, the force normal has to be vertical. What else? Okay, force of gravity. And force of gravity is always down because that's the definition. And then there's one more. What's the last one? The tension is one that I am already assuming because it's already drawn. Okay, the last one, the force of friction. And the force of friction is going to oppose the direction he's pulling it. If it's static, it's going to oppose the direction it's sliding. If it's sliding, in both cases, it would be to the left in this picture. So there we've identified all of the forces that are acting on the object. They're not all the forces available to us, but they're only ones that are acting on the object. So now we have to choose our coordinate system. So now somebody in this classroom in Union, what would you choose for your directions for your coordinate system? Okay, X is technically not going to be a direction, but he also had his arm out. So that was a direction. Horizontal is a good direction to choose for one of your coordinates because it's going to accelerate in the horizontal direction. So we stick with horizontal as one of them. And so I will define our traditional XY coordinate system with X is horizontal and Y is vertical. Now this is not going to be universal in all problems, but it is for this one. So then what is the condition for the cube sliding? How is that different from the condition for part A, it's what force is necessary to get the cube to start to slide. So the question is, what is the condition I have to meet for the cube to start to slide? Okay, overcoming friction, but it's not kinetic, it's static. Because it's initially static, and the static friction has a higher coefficient. You see here, they gave us the coefficients. The static coefficient is significantly higher than the kinetic. So you have to pull it hard enough to overcome the static friction. And you might remember when I talked about friction in class, I said usually the problems are going to give us some kind of wording to tell us that we're going to use the maximum static friction. Because if it's not sliding, you don't know what the static friction is going to be. It's just going to be whatever is necessary to keep it from sliding. So we're going to find for part A, which is my item 4 here, the condition where the force of friction is equal to the maximum value for the force of static friction. What's different about part B?
Using the kinetic.
Right. Part B, we're going to switch from the static to kinetic friction. Since the coefficient of kinetic friction is roughly 1/3 the coefficient of static friction, if you keep pulling with the force that was necessary to make it start moving, you're applying more force forward than the friction is backward, and it's going to accelerate. So now that we have our ideas put together, now we're ready to solve the problem. So I've got my coordinates, I've got all my forces. I'm just going to treat this as my free body diagram. I am going to put a subscript of A because it's the force that's being applied by the gentleman. So I added a subscript to it to make it so all my forces have subscripts. I don't have one that just says F. So I need to break these into components because I have two directions. So I'm right off the bat going to break this into a horizontal and a vertical part. And in the horizontal direction, force of friction is all in the horizontal direction. And so I'm going to put that in here, my force of friction, and I'm going to put force of friction here. I'm not going to put static or kinetic because I want to repeat this and not have to redo it when I go to part B. So I'm just going to put force of friction, and then I'll apply whichever friction it is, if it's A or B. So the force of friction vector, I said it's all in the horizontal direction. In fact, it's all in the negative x direction, so I'm going to put negative out front. Force of friction, the equation, I'll write the equation up here. The force of static friction is less than or equal to mu static times the force normal. The force of kinetic friction is equal to mu kinetic times force normal. So I have two different equations, but we were given the condition where we're going to have maximum static friction. So I'm going to put equals mu times force normal, which will be true for both cases, given the restrictions on this problem. In the vertical direction, my force of friction, it was all horizontal. So what does that tell you for the vertical direction? 0. So I write there explicitly so I don't look back and think that I forgot something. Now, when you look at this, oftentimes students aren't super comfortable here because I have symbols in there. Well, I do have a value that I can put in for mu for part A and a different value I can put in for mu for part B, but I don't know the force normal. And so I have no choice but to put a symbol here for now. I will have to solve to find force normal. Okay, second force. Let's go with force normal. What direction is force normal pointing? Up. It's exclusively up, so how much in the horizontal? 0. So that's going to be easy again. The force normal vector is equal to 0 in the x hat plus, because it's up, force normal magnitude in the y direction. Third one I'm going to go with is gravity because it's vertical again. But now it's down. So my force of gravity, 0 in the x direction, minus mg in the y direction. I put in mg because we know force of gravity is always equal to mg. So I can put that in. And we know m, given right there. And of course, g we know is a constant. We'll use 9.80 for g. Now I'm left with one more force, the force applied. The force applied has two components, one horizontal and one vertical. So this one I have to actually do the work of breaking into components. So here's where we consult our trigonometric functions, and I'm going to break this into two pieces. Okay, make my vector so it goes all the way there. Those two pieces, here's my force applied x, here's my force applied y. Is my force applied x in the positive or negative x direction? Positive. My force applied y is either positive or negative y direction? Positive. Okay, so I have both of them positive. I want to make sure I get those signs out of the way so we don't have to worry about that. Then my force applied x is the adjacent side. Y is adjacent because it's making part of that 25-degree angle. And so with my trigonometric functions, cosine of the angle will relate hypotenuse and adjacent, specifically cosine of theta equals force AX over force A. Now notice I use theta. That will come, oh boy. That will come up in today's lecture is how the symbols we use for measuring angle. So it's just a generic, we use theta as a symbol for angle, just like we use X as a symbol for distance. V is a symbol for speed. So it's just a common definition or designation. So if I take this equation I wrote for cosine and solve it for force A in the X direction, all you have to do is multiply force A on both sides. And I have force A cosine theta. And for the Y direction, we already determined it's plus force A sine theta in the Y direction. So now I've broken the forces up into components. It's important that we go back and remember what I'm doing, because it's taken us, 10 minutes to get this far? And we might have forgotten what the problem was. So what we're trying to do here is calculate what that applied force has to be. So the F sub A, as I called it, is what I'm looking for. Now, if I look at my vertical and horizontal directions, you see that F of A is right here, and it's also right there. So I have that force I'm looking for both in my horizontal and vertical directions. What else do I not know besides force A? So I'm going to underline everything I don't know. What else do I not know? I don't know the force normal. Now at this point, a lot of people, if you've just done a few physics problems, oftentimes that force normal turns out to be the weight. And they say, oh sure, force normal is mg. And they're wrong. You have to make sure you pay attention and you actually calculate the force normal. So if I look at this, I have two equations, two unknowns. One, sum of the forces in the X direction. One, sum of the forces in the Y direction. So I'm going to have to use Newton's second law both in the X direction and the Y direction, and then I'll be able to solve for the force applied. So let's go ahead and do that. Oh, one other thing I should have written down that I didn't. What's the acceleration for part A? 0. Okay, for part A, the acceleration is 0 because we're finding the force necessary to just get it to start moving. Now, one could say, but if you get to start moving, it's changing speed, so the acceleration is not 0. But you're finding the separation between having acceleration and having no acceleration. That separation point has an acceleration of 0. So that's another important thing we have to have. That's acceleration in the X direction for part A is 0. Acceleration in the Y direction for part A is 0. So let's apply Newton's second law. Sum of the forces in the X direction is equal to mass times acceleration in the X direction. Now I don't need to put my X hats anymore because I have specified I'm looking only at the forces in the X direction. So by putting sum of the forces in X, that specifies I'm looking at the ones that had X hats. I don't write them again because then it'd be vector still. So looking up, I just have my column. I always like to put positives before negatives so I don't have an extraneous minus sign. So I'm just going to put those in there. The left hand replaced from the column. So the left hand becomes FA cosine theta minus mu Fn. And then the right side is going to be the mass times the acceleration in the X direction, which was 0. And so right away I get a simple equation. FA cosine theta is equal to mu Fn. Now I'm going to leave it like that for now. I might need to solve it for something, but I want to see what I get on the other side before I decide where to go with it. So look in the other side. Sum of the forces in the Y direction is equal to MA in the Y direction. Looking at the column above, once again, I just take force normal minus mg plus Fa sine of theta. So that's all the things in the column. That's the sum of my forces in the y direction is equal to, and the acceleration in the y direction was 0. So now I have another equation, and I need to combine these to eliminate one force. Which force am I eliminating? Normal. I had two unknowns, the force normal and the force A. You can't tell that was underlined anymore because I drew no line on top of it. And so I want to eliminate force normal so I can find what force A is. So I'm just going to take this and solve it to say force normal is equal to mg minus force A sine theta, and then put that in there. Now I have an equation with only one unknown, and I can solve for Fa. I am actually at the bottom of this sheet, so I'm going to have to make another blank page to work on, but I can at least simplify it a little. I'm going to have to move this term with the Fa over to the same side as the other term with the Fa, so I'm going to have to add mu Fa sine theta to both sides. And so this gives me, if I factor out the Fa, I have that equation, which for the final step, you divide both sides by cosine theta plus mu sine theta. Now, I guess if I'm going to do part B, it probably would behoove me to actually find a number for this because, well, I'm going to, yeah, let's find a number. What can you not see? Oh, actually, I did discover there's a way for people in the Southwest there to hide, but I probably have that written where you can't see it, don't I? What can you not see?
The corner.
The same thing? This here?
Yeah.
Okay. Can
They can see it through the camera. They should be able to see it when they see you.
So somebody have a calculator to calculate this for us. The mu is, I better put the numbers in here for you. 0.1 times 41 kilograms. I'm going to put times g to save me time, 9.80, divided by cosine of 25 degrees plus 0.1 sine of 25 degrees. And while you're calculating, you're going to make it
42.358.
Okay, so a student said 42.358 newtons. A quick question here, is that more or less than the weight of the brick, of the ice? It's actually way less because the ice is 41 kilograms. You multiply it by 9.8 meters per second squared to get its weight. This is about 1/10 the weight. Well, it's more than 1/10, but it's much smaller than the weight of the ice, which is because it's sliding. Now, if we compare it to the force of, well, actually, let's not go there. I'm assuming that you did that calculation right and that I didn't make any sign errors because I actually thought it would be a smaller number than that. It's correct. Okay. So we have two people. Let's go on and look at the second one. And if I made a mistake, at some point, I'm sure somebody's going to say, hey, you did this wrong. And I will admit my mistake if I did. So now for part B, what is the acceleration if it starts to move and we maintain that force? So now I'm going to come back here and I'm going to be able to use this relationship to find the force or the acceleration, but I'm going to need to know what the force normal is to do that. We didn't calculate the force normal, we just eliminated it, right? Well, now I have to actually go back and calculate it so I can put it in. So let's calculate the force normal. So from this equation right here, we actually have to get the number. Minus and what do we have for that force normal? And this is the one that we normally would compare to the force of gravity.
I get 383.889.
383.899. Is that what we said?
Yeah.
Okay, so I'm just going to put 9 newtons. That's 2 extra sig figs. Now, this 383.9 newtons is well less than the force of gravity. The force of gravity is about 400 newtons. So why is it that the force normal is less than the force of gravity for this situation? Okay, because the force applied is partially pulling up. So what's holding up the ice is not just force normal, it's force normal and part of the rope that are holding it up. So that's why force normal is less than the weight of the ice. That's why we couldn't solve this problem by just assuming force normal was the weight of the ice. Okay, so now for part B, what is its acceleration if we keep that force? So now I can just come over here and say sum of the forces at x is max. So I'm going to go to the next page and work with that. And this is going to be mu kinetic now instead of the mu static. So the second line is just repeating what I had right here, except instead of putting 0, I put max. And so now we solve this for ax by dividing everything by m. I don't remember the number. 358. And so there we'll get what the acceleration is. So I'll wait and get that number before moving on.
.655.
So there we have the acceleration it's going to have if I keep pulling with the force that was necessary to make it start sliding. Okay, so going back to this, the reason I went ahead and did this problem, even though it's not due yet, I know I did it last time too, is because it really illustrates how you use Newton's second law, breaking things into components, and it illustrates that you can't just say force normal is mg. So does anyone have questions about this solution? Use half the class on this. Isaac has a question.
For force normal, if if we're applying a force, like for example, since we were applying a force in both an upward and a horizontal direction, is it safe to say that we should always double check our force normal? Or are there certain situations where we can assume that force normal kind of negates force gravity? Or is the same as force gravity?
So the question was, are there some cases where we can be safe in just saying, yeah, the force normal has to be the same magnitude as the force of gravity and not have to go through the work? In the cases where that's true, it's usually so glaringly obvious that it would only take you like 10 seconds to say, okay, I only have two forces in the vertical direction. You don't have to show the work if you just have the two forces, because that's going to be the output. But if you have more than two forces in the vertical direction, then you're going to have to go through the process. So there's your situation. If there's only two, then you know. And of course, if it's on a slant, like another problem we might get to, well, then you have a different situation to deal with. Okay, two more slides before I start with rotational motion. One about real life versus the idea we've been talking about with free fall. I've mentioned multiple times that in real life, you have air resistance. And the air resistance depends on the type of fluid flow. If you have a smooth fluid flow, we call smooth fluid flow laminar, because you have the fluid just is going around in sheets, lamina. Lamina means sheets. If you have smooth flow like that, then you have Stokes' law that gives you the force of air resistance. And that force is proportional to the speed of the air blowing by the object. If you have a turbulent flow, so turbulent flow, you have eddies and vortices that are caused because it's going by so fast. Then you have this drag force equation that's proportional to speed squared. So the actual air resistance, how it depends on speed, depends on if you have laminar flow or if you have turbulent flow. Let's say you're doing something like driving a race car. If you're driving a race car, the thing that's slowing you down, besides your brakes, of course, is air resistance. And so if you can make it laminar flow, you'll have a much smaller air resistance. And so there's a lot of work that goes into designing the aerodynamics of these cars to try to reduce that air resistance to make it as close to laminar as possible so they have less force going against them. Oftentimes, in a related note, people wonder why you have to have your engine running to keep your car going 80 miles an hour down the freeway. And the reason is simple. Even if it's a nice, level freeway, you have two things that you have to overcome. A very, very minor thing, that's the rolling friction. Your tires on your car, you don't inflate them so they're hard as a rock. You inflate them some, but they actually flatten a little bit when they're on the ground, and that flattening is designed to make them squeeze the ground and get a little better grip. So if you overinflate your tires, you'll actually have less rolling friction because they're not going to be squishing down, but you have less traction. That's a really small effect. The big effect is the air resistance. So you are having to move air out of the way with the car, and that's why you're expending gasoline to keep going at a constant speed. Okay, the last thing here is talking about stress and strain. I am not going to do much work with this at all, but I have to at least introduce these things. Stress is force divided by area. So if I have a force acting on a surface, such as I am presently standing on the ground, well, let's go with something simpler. I have a mass here. I place the mass on my rotating platform. There is a downward force of gravity acting on that mass. The mass is touching the table, so it also has an upward force normal acting on it, right? So that's a situation like Isaac was asking. You only have two vertical forces. I can do Newton's second law in my head and say the force normal is equal to the weight of that mass, which in this case is 9.8 newtons. Now I'm going to look at this surface, the surface of the platform. that platform has a downward Newton's third law force from the weight pushing in on it. And that force is distributed over the area of this base. And so the stress that it is putting on that is the force that it's applying, the 9.8 newtons, divided by the area of that base. So that's what stress is, the force divided by an area. And you can instantly see things like, so if I, who weighs a lot, am wearing my size 13.5 shoes, my force is being fairly spread out. If Brandy, who weighs a lot less than me, was wearing spiked heels and she leaned back and just put all her weight on the spike of a heel, her much smaller weight would be on a very small area, the result being a much higher stress produced by her high heel than produced by my foot. And so you would much rather have me step on your finger than have Brandy put all her weight on that heel on your finger, even though there's a lot less force involved with Brandy. So that's an introduction to stress. Now, stress is technically a tensor. I'm guessing I have 2 or 3 people who've actually studied tensors. You studied them in linear algebra. What does it mean to be a tensor? Well, a vector, you have just one set of directions. A tensor, you have multiple sets of directions. And stress as a tensor has multiple sets of directions. Now, I see people writing down, this will not come up on a test. Okay. But you have different types of stress that go into the stress tensor, and the different types of stress will come up on a test. So what are the different types of stress? The first is the stress where the force is going into a surface. So right now I have the weight of that mass going down into the surface, and we call that a compressive stress. So it's compressive when the force is into the surface. And it's really easy to think about because it's compressing the material. A tensile stress is a stress that's in tension. I would have to do something like take my hand, put some Gorilla Glue on it, and slap my hand on the table. After it dries, if I try to pull my hand up, then the force is going out of the surface. And so that's what the tensile is when you have force, I forgot the word out of surface. Which once again is easy to think about it because it's putting it in tension. And the final type of stress is the shear stress. So once again, if I have the Gorilla Glue in my hand, I glue it to the table, and I try to slide my hand sideways, then I have what we call a shear stress, where the force is perpendicular to the normal, or the force is in the plane of the surface. So the two pictures here show, well, let me just ask you, which kind of stress is shown in figure A? Is that, which one of the three? Okay, Mahala has an answer. Which one? Tensile. Okay, tensile. And she's right, because the force is coming out of the surface. Now, the second one is just the opposite. The force is into the surface, so what do we call that? Compressive. And so what direction would the force have to be if it was a shear stress? A force like that would make a shear stress. Now, there's a second thing here besides stress, and that's strain. Strain is the result of the stress. I think I've probably mentioned this already, but when I was in graduate school, there was a lot of stress in graduate school. In this case, it's mental stress, right? But to me, it very much applies to the physical stress. You have all of this information that you're trying to cram into your head, And, well, it causes people to do funny things. So I had one classmate who came to a test, and she had all of these sores on her face. And I was like, what happened? And it was when she was studying, she was just sitting here mindlessly scratching her face and gouged her face up. That is a strain. That's a response to the stress. The stress was having to know this information. The strain was how her body responded to that and made her do that. And oddly enough, her boyfriend had no eyelashes because when he was staying, he was going until he pulled them all out. That is a very classic example of stress and strain outside of physics. In physics, if we have elastic behavior means if I deform something, it comes back. So I could, for instance, take my little tennis ball and say if I squeeze the tennis ball, when I let go, it comes back. So that was elastic behavior. If I have something like the paper clip and I bend the paper clip, it didn't come back. That's what we call plastic behavior, plastic deformation. Plastic, it was permanent. So if I have elastic behavior, the stress and strain are linearly related to each other. So you have this equation right here that says the stress, that sigma, so lowercase sigma, is the symbol for stress, is equal to Young's elastic modulus, that's a Y, it's not like a epsilon or something crazy, times the strain. Now I'm going to use the symbol shown above because you'll see this comes down to something that you've already seen. So this is, if I use a compressive or tensile stress, force over area is very simple. It's equal to Young's modulus times change in length over the original length. If I take this equation and I solve it for force, I get this equation. That is an equation we've already seen. It was called Hooke's law. I didn't use the words Hooke's law in the lecture, but it's the equation that defines how springs respond. Because a spring is elastic. You stretch it, it comes back, unless you stretch it too far. If you go past the elastic limit, then you have plastic deformation and it's permanently deformed. And so they are illustrating Hooke's law, the standard elastoplastic behavior with Young's modulus. So I'll probably give you one homework problem where I have something like you have a Young's modulus of blah. You put this force on this surface, how much does it stretch or compress? And you just use that equation, stress is equal to Young's modulus times the strain, to get your answer. Mahala has a question.
So what's the difference between stress and pressure?
Okay, very astute question. Mahala asks, what's the difference between stress and pressure? And the difference is significant yet often overlooked. Pressure is force over area. And so Mahala looks at this and says, that's the definition of pressure. But pressure is the same in all directions. So instead of being a tensor where you have actually 6 unique stresses you can define, for pressure you just have one value. And the force is always going into whatever the surface is. So you can never have a tensile equivalent to pressure. You can never have a shear equivalent to pressure. Pressure is always compressive. So pressure occurs in fluids, stress occurs in solids. So it's a really good question. And we will study pressure a lot more carefully. Okay, now we're ready for circular motion. Got 10 minutes for this, and I got 2 problems I thought I was going to work out. This is just an introductory slide. Skip the introductory slide. Measuring angles. Why do we worry about measuring angles in rotational motion? Because if we have a rigid object, so notice I have the word here, rigid object. If we have a rigid object, then everything in that object is going to have the same time to do one cycle as if it's rotating. So we call that time to do a cycle a period. They'll all have the same period. But of course, if you're close to the center, you do a smaller distance than if you're far from the center. So we'll get a few definitions here, and then I'll go to a demonstration. We measure the angle like you know how to measure an angle. But there is a relationship between the angle and the arc length. This delta S is an arc length. An arc is a piece of a circle. And the relationship between that arc length and the angle is shown right here. The angle is the arc length divided by the radius. Now, if you look at this, the first thing you should notice about this equation is the units. What are the units of arc length in the standard metric system? Distance. Arc length is the distance of that green line. Meters. So the units for arc length are meters. So I'm going to have units of meters on top. And what's the unit for the radius? Meters. And so that's no units. Angle is a unitless measurement. How many people knew the angle was unitless? I have a few hands. Most of us think, well, there's 360 degrees in a circle. Degrees are a unit. Or there are 2 pi radians in a circle, and radians are a unit. Well, let's look at where these come from. If you do a complete circle, what's the circumference? It's pi times diameter. I'm going to put that in terms of the radius, so it's 2 pi r. So if I do a complete circle, LE, the arc length is equal to 2 pi times the radius, which means that the angle for the complete circle is 2 pi in the unitless angle. We give it a name, we call that radians. The unitless angle is called radians. But that means that radians can appear and disappear like magic, because what they're saying is, I measured an angle and I measured it in the natural unitless units. So when you have an equation, you can drop the radians or add the radians basically as you see fit. If you're listing something that has to do with an angle measurement, make sure you put radians in there so people know. I use the natural unitless unit. Well, then what's the point of the degrees? And because I only have 8 minutes left, I'm going to go right to answering and not asking if anybody knows. Degrees are based on how much the sun appears to move from one day to the next as we observe it from Earth. Now, we know the Earth is really the thing going around the sun. But back when this idea was put forward, they thought that the Earth was going around the sun, the sun was going around the Earth. And so they measured how far the sun moves compared to the stars each day and said that's a degree. And now anyone that knows anything knows that even way back when, people knew that a day was a little bit longer than 360, or a year was a little bit longer than 365 days, right? A year is 365.2422 days long, with a little uncertainty there in the last digit. So why did they not put 365.24 degrees in a circle? Because they thought there must be some inherent magic to the number 360. I've seen people who know nothing about math posting things like this on Facebook. Why? Because 360 is evenly divisible by 1, 2, 3, 4, 5, 6. You have to skip 7. 8, 9, 10. You have to skip 11. And 12. So all but 2 numbers between 1 and 12 will divide 360. And they thought that must make it a powerful number, much better than 365.24. And so that's why you have 360 degrees in a circle. So you need to be able to convert between those 2 units, radians and degrees. Direction. Many of you have taken organic chemistry already. And in organic chemistry, when you talk about chirality, you worry about things like, is it S or R and things like that, right? Those are applications of the right-hand rule. The right-hand rule is a rule to determine a specific direction for rotation. And so the way the right-hand rule works in this first iteration is you take your right hand and you simply wrap your finger the way things are rotating, and the direction your thumb points is the direction we apply to that angle. So in this case, the picture shown, if it rotates in the direction of my arrow, then I would just take my right hand, wrap it around the axis in the direction, wrap my fingers the direction that it's going, and my thumb says that the angle is coming out of the screen toward you. If it was, so counterclockwise is coming out, and coming out we usually identify as positive. So counterclockwise angles are positive angles. Hence, in physics, we pretty much always measure our angles counterclockwise because that's the direction that we define as positive using the right-hand rule. Now, we're going to learn, by the time we finish second semester, we'll have like 5 different variations on the right-hand rule. And so there are many other variations on it coming about. Something that's important to note, your right hand and your left hand are mirror images of each other. If you try to use your left hand, you get the opposite result. Back when I was in college, I had a classmate, the teacher's teaching us this. And we're all sitting here with our hands, twisting them up, and Saeed's using his left hand. And the teacher says, Saeed, you need to use your right hand. He says, but I'm left-handed. That doesn't make your left hand look the same as everyone else's right hand. Right? So you need to use your right hand. And actually, he had an advantage because he could sit here and write while he was using his right-hand rule. For those of us who are right-handed, we have to put down the pen and twist our hand around, and then we can go put down, write again. So one case in life where sinistrality, that's where the S comes from in your, organic chemistry stuff, is a benefit. I have a left-handed cousin who has a shirt. Sinistrality is not a 4-letter word. Because left, of course, is a 4-letter word. It's a joke. All right. Motion. Points rotating will have different arc lengths depending on the radius. So let's shift over here to camera view 6. I think that was it, wasn't it? Who said yes? It was. Was it you, Alex? Oh, okay. I thought it was somebody else. Okay, so here I have a rotating platform. And on the rotating platform, I'm going to put 2 identical stoppers. One of them close to the center, one far from the center. As they go around, it's pretty clear which one's moving faster. The one on the outside. Simple reason. What's the reason why? Farther distance in the same amount of time. So the speed is the distance it has to travel. So in one full cycle, 2 pi times the radius, divided by the time for it to travel that distance, which we call the period. If I speed this up, what's going to happen to those stoppers? They might fly off. Okay, so I'm going to go with Rachel. They might fly off. If one of them is going to fly off, which one do you suppose will fly off first? Okay, everybody says the outside one. Why do you say that? Okay, it's traveling faster. First, we're physicists here. We have to do an experiment to see which one it is. And indeed, it was the outside one. Hooray, you all guessed right. Oh, I wouldn't say guess because you had knowledge about this. So the outside one flew off faster. Now let's think about what was going on. Why is this one not flying off? It's not moving as far, but why did the outer one move? It was moving farther. Something was making it so it was trying to not stay put. So there had to be a force, we think. Now I have to preface this with that's wrong. But we think there's a force. But there was a force that was keeping it from sliding off. And what force was keeping it from sliding off? Friction. So friction was keeping it from sliding off. And we tend to think there was a force trying to pull it off. You had a question, Jordan.
I was going to say, would it be because of the inertia holding it, or wanting it to continue in the direction of most traveling?
And Jordan went straight to the correct answer. It's inertia. Oftentimes we have, this is, by the way, I forgot to talk about this because I wanted to get to that. The speed of anything is going to be the change in arc length over change in time. But since we had theta, delta theta was equal to delta S over R, then that means delta S is equal to delta theta R. Put that in here. And we define omega is the change in angle divided by the change in time. Omega is called the angular velocity if it's a vector, getting the direction for the right-hand rule, angular speed if it's a scalar. And so the relationship between speed and angular velocity is omega v equals omega r. Okay, going to the words that go with what Jordan said. I'm going to end in just, I think, one slide here. Oftentimes people talk about a centrifugal force. But centrifugal force is fictitious. It doesn't exist. It is actually inertia that was making things try to go. If we think to Newton's first law of motion, an object in motion stays in motion unless a net force acts on it. So this stopper, if it's going around a circle, at the instant it gets right here, its velocity was that direction. It wanted to stay in that direction. That's its natural motion. And so you had to have a force to change its direction. And so inertia would have just had to go like this. But there was friction, and the friction was making it so it didn't slide and went in a circle. So there's no centrifugal force making it push outward, but there was a force supplied by friction here that was pulling it in to make it go in a circle, and that's what centripetal acceleration is. Centripetal acceleration, which has an equation of, we're not even going to do the question, or the clicker question, obviously, for time. The centripetal acceleration is the speed squared divided by radius, or the angular velocity squared times radius. So one student pointed out in section 6.2, the concept coach questions, there were two similar questions. One said they had the same omega, one said they had the same speed. So you need to pay attention to those differences between speed and the angular velocity. And the centripetal acceleration is the acceleration necessary to change its direction while maintaining a constant speed. Okay, I went 2 minutes over, sorry. Have a great Monday. And remember, tonight, 7 p.m., Bissell versus the Burners at the football field.